Okay, so welcome to this final video on kiss and run fusion. In this video, what I want to do is explain a slight modification of this experiment that we saw that Chen did, which even further confirms the kiss and run fusion theory. Okay, so basically, what we can do is we can use things known as quantum dots. And don't worry, that has a very intimidating title, but these are not scary things at all. Basically, what a quantum dot is it's a particle which is around 7 to 8 nanometers in diameter. Okay, so it's a little particle which is fluorescent. Okay, so it's just some chemical species that is around that size. I'm not specifying what it is because it doesn't specify what a quantum dot is. It's just some small protein or some such structure which has a diameter of around 7 to 8 nanometers and is fluorescent. So this is very highly fluorescent. Very highly fluorescent. Right, so what are we going to use these quantum dots to do? Okay, well, we can use them to do the same thing as we did with this Chen experiment. So what we're going to do is we're going to take an axon terminal here, and again what we're going to do is bathe it in another one of these FM dyes, and I think the dye they actually used when they did this wasn't FM143, but was a very close analogue of FM143, FM464 they used. Okay, so FM464 is effectively another dye exactly like FM143, which binds to plasma membranes. We'll draw it in orange this time to denote that it's different from FM143. It binds to plasma membranes, and therefore, when this axon terminal endocytoses a portion of the plasma membrane in order to recycle that plasma membrane to make more synaptic vesicles, it's going to get a whole coat of this FM464 here. So here is our FM464 lining our synaptic vesicle. Okay, now we're going to also put these quantum dots into this liquid that we're bathing the axon terminal in. So here are our quantum dots. Now what colour should I draw these quantum dots in? Turquoise, I think. And what's going to happen is that potentially, when you endocytose this membrane, you might just happen to get a quantum dot in you. Okay, and generally this actually does happen. Generally, when you endocytose a synaptic vesicle, they generally do capture these quantum dots. So what you're going to end up with is synaptic vesicles which are lined by this FM464, and which also have a quantum dot right at the center. Now, why is this going to help us? Well, again, what we're going to do is repeat our experiment that we did with the Chen experiment. So we're going to wash away all of this FM464 that's bound to the plasma membrane. We're going to wash away the quantum dots that are in the fluid that the axon terminal is in, so that now what we have is just an axon terminal where the synaptic vesicles have this FM464 dye in them, and also these quantum dots. So here are our synaptic vesicles now bound to the presynaptic membrane here. They have the FM464 dye lining their membranes here, and then they have the quantum dots right at the center. Okay, right. So why is this useful? Well, basically what we can do is another total internal reflection fluorescence microscopy experiment. So we're going to stick it on a glass plate effectively again. So here is the glass plate, and we're going to fire radiation again at the glass plate. We're going to get total internal reflection again, and we'll get our evanescent wave propagating into the first 300 nanometers of our axon terminal here. So here comes our evanescent wave. Now the evanescent wave, this energy of the evanescent wave will excite both the FM464 and also the quantum dots. So they'll both start fluorescing. So we then collect this radiation, and we have a picture of this slice of the cell. So let's draw the picture that we have. So we're going to basically see, if we look from the bottom at the moment, what we're going to see is our axon terminal with these synaptic vesicles which have this FM464 and also a quantum dot in them, basically. Now, this is the brilliant bit. When we excite this this axon terminal, and we start getting the exocytosis of these synaptic vesicles, then what's going to happen? Well, in full fusion, so actually let's draw it out step by step. So if we have initially we have our synaptic vesicle docked at the presynaptic membrane, then what forms is a fusion pore, okay, and then what can either happen is it can go on to full fusion, like so, and in that case what you're going to see is the FM464 dispersed on the membrane, but the quantum dot isn't bound to the membrane, so it will just diffuse off potentially. Okay, so that's how you can see full fusion. You'll see an increase in the orange dot, basically, as the FM464 now spreads out in the plasma membrane, and also the fact that the whole surface area of the synaptic vesicle is now flat, basically, rather than curved around in a sphere. Okay, and you might see the quantum dot diffuse off. Whereas if you get kiss and run fusion, what are you going to see? So what will happen is you'll supply a little bit of the membrane into the plasma membrane, but the quantum dot, that can't get through this fusion pore, basically. The quantum dot is too big at 7 to 8 nanometers to get through the fusion pore. So, if you get kiss and run fusion, what you're going to get is a little bit of the FM464 coming out, okay, into the plasma membrane. And again, you'll probably have to be able to see that from taking a picture from a different angle rather than from below, as I'm showing here. But you'll see a little bit of the FM464 coming into the plasma membrane. So for instance, if you took a photo from this angle here, okay, you can imagine that you'd be able to see this orange dye going into the plasma membrane here. Okay, right, so you'll see the FM464 going into the membrane, but you won't see the quantum dot leaving, and that would indicate that you haven't had full fusion, and instead you've just had this kiss and run fusion where a little bit of the plasma membrane has gone into a little bit of the synaptic vesicle membrane has gone into the plasma membrane, but the fusion pore is too narrow for the quantum dot to get out, so it's remained in the synaptic vesicle. And indeed, this is what you see. You see the quantum dot remaining there whilst some of the plasma membrane from the synaptic vesicle goes into the cell membrane. Okay, and that's a nice confirmation, basically, that kiss and run fusion exists. Despite all this evidence, there are still non-believers. I think if you got what I've been told is that if you got a consortium of neuroscientists, okay, and you asked them whether they believed in kiss and run fusion, 9 out of 10 now would believe in kiss and run fusion, but there are still the skeptics.